Hello everyone, this is me, Susan's System. Thank you for tuning in. I am very excited about today's video. Without a further ado, let's dive in. In the previous video, we discussed about the approximation of log function using the Taylor series and other methods. But today, we are going to approximate it using neural network, specifically feed-forward network. Okay, so what we are seeing here is a simple architecture of a single layer hidden network where we are using this architecture to approximate the log function. Okay, so let's have a look at the input where I constrain the range of input between the 0.1 and 100, and I randomly sampled 10,000 samples within that range for the input. Okay, so for the input of log function, I have chosen the range 0.1 to 100 of sample size 10,000. Okay, and this goes to a single layer hidden network and outputs a single value of size 1. Okay, and I am fixing these hyperparameters to learning rate 0.001, batch size 832, and epochs to 100. Let's have some code. I've already written the code so that I don't want to waste the time on it. Okay, let's import some libraries that we're going to use, and here is the input that I have randomly sampled between the range 0.1 and 100 of sample size 10,000, and this is the Y train, which is the actual log value. Okay, let's initialize the input values. This is the single layer architecture we are using. I don't need to explain each and everything about it. Let's initialize the model. Now I'm using only a single layer. Okay, here I am using a loss function as a MSE loss, okay, and optimizer as a Adam optimizer. Okay, now let's train the model with a batch size 32 and epochs 200. Okay, the model is training here. Okay, we have successfully trained the model to 100 epochs with a training loss of 0.10. Okay, now let's initialize the test values of size 100 samples. Okay, and have some visualization how our model predicted. Okay, this is how our model predicted, where these blue dots are the actual log values. We are familiar with this shape, right? The log shape, but this red is the predicted values from our model. So what we can see here is our model is fitting a line, not a curve. Okay, can it fit a curve using a more hidden units? Because we are only using a single hidden units. Okay, we have only passed a single hidden units. Can it fit a curve? Because it is only fitting a line here. Okay, can it? Okay, it's only fitting a line here. We have to fit a curve. Okay, we are going to change to 64 and run this model. Train it again. Let's wait. Okay, our training is completed. Let's reinitialize the test values and let's visualize how our model performed. Okay, so what we can see here is our model is unable to fit a curve. It is still fitting a straight line. So we can conclude that increasing the hidden size didn't affect the model to fit the curve. It is not fitting a curve, rather it is fitting a straight line. So what is the caveat here? It is because we didn't use any non-linear activation function. We haven't used any non-linear activation function here. Okay, let's see here. We are only using a linear units. We have only used a linear units here. Now we have to incorporate a non-linear feature in our model, right? So how can we do that? We can use some popular non-linear units. We're gonna use a ReLU. Self dot ReLU equals to m dot ReLU. Okay, I'm gonna incorporate it between the layers dot ReLU. Okay, now let's reinitialize our model, a function. Now our model, let's experiment how our model perform when we only use a single units, hidden units. Okay, first we're gonna experiment that. Okay, we have initialized that. Now let's train it. Okay, our training is nearly completed, but I can see here the training loss is still not sufficiently low. Okay, it's still 0.10, which is a very large for the log function. Error. Let's see how our model performed using the non-linear activation function. Okay, this is how our model predicted. It is still fitting a line. Okay, it is not still fitting a curve, rather it is still fitting a line. Okay, so let's increase the units, our hidden units, to 10, from 1 to 10, and see how it performs, because we have seen that using a single hidden units and incorporating the non-linearity feature didn't help so much, because it is still fitting a straight line for a curve. Let's train them. Okay, we can clearly see that our training loss has significantly decreased. Okay, previously it was 0.1 something, now it has decreased to 0.0015 using 10 units. Now let's see how our model performed. Bang! Finally, our model learned to approximate the curve rather than fitting a straight line. In all of the previous cases, it was fitting a straight line, as we have seen. Now it fitted a curve with a marginally small error. Okay, what we have seen here is that when we incorporated the non-linearity feature in our model with sufficient hidden units, our model was able to learn the log curve. Okay, our model was able to fit the log function curve. And also we have empirically proved the universal approximation theorem. Okay, what we have done here is that we experimentally proved the universal approximation theorem. In summary, when we use enough hidden units with at least one hidden layer with activation function, then we can approximate, or we can map any Borel approximation function. Thank you everyone. Today we have empirically or experimentally learned a universal approximation theorem. For today, it's a goodbye for me. We'll meet in the next video. Stay tuned for that. Bye bye.